Hi. In the previous segment, we introduced Dedekind's definition of infinite sets and gave the cardinality of countable sets. That is, the sets equinumerous with the natural numbers, the name Aleph 0. In this segment, we shall look at the size of some other infinite sets. Let's begin with a set of integers, z. That is, the natural numbers and the negative numbers taken together. It would seem that this means there are almost twice as many integers as natural numbers. Let's look at this. What this shows is a way in which the integers can be enumerated. In other words, this animation shows the beginnings of a procedure that, one by one, lists the integers in such a way that every integer, sooner or later, will end up on that list. Put another way, if for any integer you interpret its position on that list as the natural number it maps to, what this enumeration does is construct a bijection between the natural numbers and the integers, showing that both sets are, in fact, of equal size. That is, it shows that the integers, too, are countable. What this means is that doubling the number of elements in a countable set does not actually change the number of elements in it. This, incidentally, would be the bijection that this animation alludes to. As we have seen, doubling Aleph 0 has no effect, and we still get Aleph 0 number of elements. Now let us look at a product of infinite sets. Let's take the product of the integers with themselves, z cross z, or z squared. For finite sets, the cardinality of a Cartesian product like this is the product of the cardinalities of the sets that are being multiplied. In this case, we multiply a countable set with itself, which means that we are multiplying a set of size Aleph 0 with a set of size Aleph 0, so expect to get something like Aleph 0 squared. How does it compare to Aleph 0? Let's start by drawing the elements of z squared in the plane. Z squared is a set of all those dots on integer coordinates. Starting with the origin at point 0, 0, we take a spiral walk around the origin. Note that for any pair of integer numbers, the walk will eventually get to it. The key here is that this allows us to eventually assign every pair of integers a natural number, namely its sequence number in this spiral walk. In other words, we have just enumerated z squared, effectively constructing a bijection between it and the natural numbers. This means that z squared is also countable, and that multiplying Aleph 0 with itself results just in Aleph 0. If you want, you could try to show this more formally by constructing the bijection alluded to in the animation, or by using CSB. It's good practice. Now let us look at the set of rational numbers Q, the fractions. First, let us review some properties of the rational numbers. The first is that they are dense. This means that between any two rational numbers, there's always another rational number. In fact, because of this, it means that for any two rational numbers, no matter how close they are always infinitely many rational numbers between them. Secondly, any non-empty open interval of rational numbers, no matter how small, has exactly as many elements as all the rational numbers combined. To see this, one can easily construct a bijection between an open interval and the entire number line, like so. With that in mind, let's see how many rational numbers there are. To get the obvious stuff out of the way first, clearly there are at least as many rational numbers as there are natural numbers, because the natural numbers are a subset of the rational numbers. So the cardinality of Q is at least as big as the cardinality of n, or Aleph 0. Now we define an injection from Q into Z squared. We do this by mapping the fraction P over Q to the pair PQ. The assumption is, of course, that these fractions are fully reduced, so we don't count a rational number more than once. Since there is an injection from Q to Z squared, it means that the cardinality of Q cannot be greater than that of Z squared, which we know to be Aleph 0. Now if we put these two inequalities together, the cardinality of Q is at least Aleph 0, and it is at most Aleph 0, therefore it is Aleph 0. So even the rational numbers do not exceed countability. There are, strange as that may sound, exactly as many rational numbers as there are natural numbers. Moving away from sets of numbers, let us look at sets of finite sequences, or more simply, strings. Suppose we have a finite set A of symbols, which we sometimes also call the alphabet. The nature of those symbols does not matter for our purposes. They could be characters or digits or something else entirely. What matters is that there are only finitely many of them. Then we use the name A star, with a star in the exponent, for the set of all finite sequences in A, or all finite strings of symbols from the set A. That set always includes the empty string, written as an epsilon, and all strings of stuff from A, as long as they are finite. Such strings are extremely important in computer science. For instance, most programming languages can be seen as sets of strings over some alphabet, just like our hypothetical superlanguage L from the problem from the previous segment. Here are a few examples for alphabets and the corresponding sets of strings. Note that unless the alphabet is actually empty, the set of strings over it is always infinite. But just how infinite? The trick here is to interpret every string in A star in a way similar to how one would interpret a string of digits. The val function is an injection of A star into the natural numbers using this idea. Since we have an injection from A star to n, and the injection from n to A star is trivial for non-empty A, it follows that A star and n are equinumerous. In other words, for any finite non-empty alphabet, the set of finite sequences over that alphabet is countable.